All right, here we go with Unit 9, Chemical Kinetics. Again, Chapter 12 in the Zoom Bell book. So chemistry happens all the time. It doesn't take a chemist or somebody knowledgeable in the sciences to make things actually chemically react with one another. Molecules are constantly changing with each other and rearranging to make new types of molecules. So chemistry happens all the time. The job of the chemist is to try to speed up these reactions. Okay? So in order for reactions in essence to be useful, they got to be able to occur at a reasonable rate. So to produce the 20 million tons of ammonia needed each year for fertilizer, we can't simply mix nitrogen and hydrogen gases at 25 degrees Celsius and then wait for them to react. Those conditions, although favorable, the ammonia would be produced eventually, are just going to take way too long. So we have to be able to manipulate the conditions in order to make the chemistry worthwhile. So we're going to start out by talking about the rates that a chemical reaction proceeds at. A reaction rate in chemistry is defined as the change in concentration of a reactant or product per unit time. So reaction rates involve both the reactant side and the product side. And here's a large equation that kind of explains that idea. The rate of the reaction, the rate and speed almost of the same thing, right? The speed usually, by the way, incorporates a distance being traveled, so that's why we don't call this a speed. Rates are, the amount of something changing over a particular time, so that's why it's a rate. So the concentration of A being a particular substance, at time T2 minus the concentration of A at time T1 divided by those same times, T2 minus T1. That gives us our reaction rate. So this equation looks a little goofy. When we see A in brackets, those brackets mean concentration of A in moles per liter. So A is the reactant or product being considered. So we could say we've got 5 moles of, sodium chloride solution, 5 molar sodium chloride solution, so it's 5 moles per liter. Or we could say that the concentration of NaCl equals 5 moles, 5 molar. Okay, so this just means concentration of that particular substance, whatever it is. Okay? All right, let's talk about a couple of factors that affect reaction rate. How can we get reactions to speed up? The number one thing is temperature. And this is based on two different types of theories. We'll talk about collision theory. When two chemicals react, their molecules got to collide with each other with enough energy for the reaction to actually take place. So you can think about these things as pool balls, like if you're playing pool. And you run them into each other and they bounce off each other. You run them into each other again and they bounce off each other. And it's not until you get them up to an incredibly high rate of speed that they'd actually run into each other and they would form and they would combine together. That some of the 8 balls parts would go with the 2 balls parts. Also with temperature is the kinetic theory. Increasing the temperature means the molecules move faster. So if we go and increase the temp, molecules are going to move faster. They'll collide with each other with more energy and thus they may form. Another thing that affects rate is concentrations. If you get more reactants, you get more collisions if enough energy is present. A third thing is a catalyst. A catalyst is a chemical that speeds up reactions by lowering what we call the activation energy. Okay? And surface area of a solid reactant, kind of like the bread and butter theory, more area for reactants to be in contact with. Okay, so if we've got more, if we got a larger molecule that's a reactant, if it's got a lot of surface area, you've got more places for the other reactant molecule to kind of attach to that reactant molecule. So you're speeding up the reaction. And also pressure of gaseous reactants or products. If we increase the pressure, we're going to put those molecules closer together. So that'll allow them to collide with each other more efficiently. All right, so let's take a look at a reaction as it proceeds from the first time, so it's 1 o'clock right here, to 2, 3, 4, 5, 6, 7, to 7 o'clock. I don't know, I'm just making that up. It's obviously not the case, right? That's 12. That's 12. Okay, AM and PM. All right, there we go. So we have the initial conditions right here. This is our initial reactant, the black sphere. And as the black sphere is allowed to just kind of jostle around in the box, it decomposes to make little red spheres, a different compound. Okay, we'll call the black chemical A, we'll call the red chemical B. So what we see over a long enough period of time is that black, the concentration of black, or in this case the number of molecules of black, actually decreases. It's going down, down, down. And the number of molecules of red are increasing almost at exactly the same rate, or they should be actually at exactly the same rate. Okay? So we can find this rate. We can find the rate at which A decreases. It's going to be this equation. The rate equals the opposite, or negative, delta A divided by delta T. And remember, delta means change. So the change in A divided by that change in time. Let's try to figure that out now for this particular reaction. Let's take a particular point here, one that's kind of easy to see. Let's say this point right here for A. We can see that at time 30 it's roughly, I don't know, about 17 molecules at time 30. And then over here at time 50 it's about 10. Okay? So here's what we have got. We've got the opposite of delta A, so the change in A, that's going to be 17 minus 10, actually 10 minus 17, because we want to do them in the right order. You'll see why we want to do them in the right order in a second. Divided by 50 minus 30. So we've got negative 7 divided by 20. Okay, with this negative sign out front, right? Actually, like this. Our reaction rate, I'm going to erase this so I have some room, is a negative 7 over 20. We've got the opposite of that because of the negative sign right here. So we have 7 over 20 is the rate of reaction. Whatever that is decimal. Okay, that's the rate at which A is decreasing. Okay, A is decreasing. That much concentration, okay, per second. So let me get 7 divided by 20 here real quick. I just can't stand fractions, sorry. 7 divided by 20. Is 0.35. So this equals 0.35 moles per liter per second. So you're going to reduce this much concentration per second. So if you started at 2 molar, after 1 second you're going to be 1.65 molar. After 2 seconds you're going to be 1.3 molar, etc., etc., etc. Okay. Now we can see the opposite's the case for B. B is increasing. Okay. Now you might be wondering, why is this negative sign out here? This negative sign we put here for the decreasing reactant, so that our overall final number, as you saw like in the last one, is 0.35. We want all of our reaction rates to always be positive. Okay. We know that this is for the reactant that's decreasing. We don't want to say it's negative point. There's no such thing as a negative 0.35 concentration. So we want all of these numbers always to be positive. So that's why that negative sign comes into play over there. All right. So that type of rate that we just calculated is a rate over a particular period of time. But we can also calculate an instantaneous rate. That's just the value of the rate at any one set in time. Like right now, what's the rate? This can be obtained by computing the slope of a line tangent to the curve at that point. Okay, so again, we're going to take this particular image that we just had with the last one, and I'm just going to draw a tangent line as best I can here. Okay, it's not the greatest tangent line. I'm going to redo that. There we go, that's what I was looking for. We're going to say that it knocks it off right there. Okay, so if we want to compute what is exactly the rate at that time, we got to pick 2 points on our tangent line, right? Then we can calculate the slope of our tangent line, extrapolating our dots over there and there. Okay, so this right here, that's going to be our x2, y2. Okay, that right here is going to be our x1, y1, and then we'll be able to use our slope-intercept form to calculate m. And again, m in this case is moles per liter per second. Okay, so what are these doing? These are giving us the rates, the speeds, essentially, not speed because not distance, but the rates at which the reactants are decreasing and the products are increasing. Okay, it's important info. Now, for that previous example, though, I was just looking at one reactant and one product. Let's look at a case where we actually have one reactant and two products. Okay, this is the decomposition of nitrogen dioxide, NO2. Here's nitrogen dioxide, and it's going down, 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 decreasing, decreasing, decreasing. And as it's decreasing, it makes its two products, nitrogen monoxide, NO, up, 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 and oxygen gas. Well, one thing that's interesting to note about this particular reaction is that the decrease of NO2 coincides with a similar increase, actually the same increase of NO. Okay? But that's not the case for the oxygen. As the NO2 decreases, the O2 does not increase as fast as the NO2 decrease. And let's look at why that is. Here's our reaction. 1 mole of nitrogen dioxide gas decomposes to 2 moles of nitrogen dioxide. Actually, I got my equation wrong here. Put 2 in front there. There we go. So 2 moles of nitrogen dioxide gas decomposes to 2 moles of nitrogen monoxide plus 1 mole of oxygen gas. And what we should be able to see is that the rate at which nitrogen dioxide decreases is at the same rate as nitrogen monoxide increases, and this is because of the coefficients. Okay, again, there should be a 2 in front here. Okay, and because you've got for every 2 moles of this that are decomposed, you form 2 moles of this, well, their reaction rates should be the same. Okay, so the tangent right there would be the same as the tangent at that same exact point right there. Okay, if we had the slopes. Obviously, this one would be negative and this one would be positive, right? All right. So if you do that, if you want to prove that to yourself, you can go ahead and do so. I just did that, or the book did that for 250 seconds. So they looked at the point right about where? Right about there, right? And right about there. And they did an instantaneous rate at those 2 points. And at both of them, you're going to get 8.6 times 10 to the negative 6 moles per liter per second. Okay. Now, obviously, again, the green, the NO2 is going to be negative, the other will be positive, but that's okay. We want to get rid of that negative sign. But what we can see is that they're both equal to each other. Now, you don't even have to do math. This is kind of cool. You don't even have to do math to figure out how much oxygen increases. It's got to be half the rate at which the NO increases. Why is that? Well, there's half the amount of moles of O2 that are actually being produced. Okay, so you don't actually have to do the math. You just get, well, I guess you got to divide by 2, but you can all do that. And then there you go. That's 4.3 times 10 to the negative 6th. Please note, by the way, this is not a negative sign. Here, get out of there. Okay, 4.3 times 10 to the negative 6th. So it's half the rate at which the NO is produced. So there we go. Those are reaction rates. If you can find a slope, you can find a reaction rate. And they're pretty conceptual. I mean, I think we understand how this stuff works. Okay, we'll do a little bit of a demo on this tomorrow and some book problems to finish it up.